Father, we are starting. Is it okay, Father?
Yes.
Hello. Am I
Yes. Yes.
audible, Father?
Yes.
Father, we are starting. Is it okay, Father?
Yes.
Hello. Am I
Yes.
audible, Father? Okay.
Yes.
Good afternoon, Mentor. Here we have Dr. Reverend Father Joseph Verghese Puritra, CMI Father, Director of Research, Christ University, Bangalore, to present this invited talk before you. We are so happy to have Father over here in online, in spite of his busy schedule. Dr. Father Joseph is an expert in graph theory field, and he has conducted online and offline conferences in and around the country, national and international. He has publications more than 100 to his credit, and he is an author of many books, which is of relevance for mathematics in daily life. Last year, we were happy to have Father in midst of us for Emerging Trends in Applied Mathematics 2020, in which Father was explaining a problem which was very much related to the COVID issue. So, we are so happy to have you here, Father, in midst of us to present your invited talk in front of chosen audience in front of us. This program is being live streamed and we have many online viewers at present. We are happy to share the joy of Father to be here with NAP AA plus 3.7 grade for St. Thomas College Autonomous Station. We cordially invite Father in midst of us on behalf of the Department of Mathematics, Autonomous College, St. Thomas College, Trishur, and on behalf of the convener, myself, for ETAM 2020. Over to you, Father.
Thank you very much. Good afternoon, head of the department, faculty members, all the organizing committee members, invited guests, students, and participants. This is a happy moment to be invited by St. Thomas College, Trishur, and to be part of this conference. I would bring to your attention a recently not much worked out area in applicable mathematics, especially coming from the field of graph theory. Even from the level of MSc, students can work on it. There are many people who are working on this area, but some of the problems are those simple. It takes longer time for the verifications. So as getting the hint from here, even the postgraduate students or undergraduate students can take up some of the problems from here and try to work and get some good results, which is sometimes some of the results are even publishable in good journals. We'll show you an example for that. I would like to share my screen now. Okay. Yeah. Hope the screen is visible to you. Can you all see the screen? Hello? Can you all see the screen?
Yes, Father, it's visible.
Thank you. The title of the talk is The Line Completion Number of Graphs. Most of us have some basic idea of graphs. Some of you are experts in that. I would like your attention drawn to the fundamental concepts regarding graphs that which we are concerned about. Graph is a mathematical model that is representing relations between the members of a particular set. Being a set, every element of that is well defined, identifiable. It could be a set of people, it could be a set of any kind of objects. In case elements among themselves are connected or related, associated in some way, we try to combine them. For example, here on the screen, it could be a friendship, it could be the type of dress we use, it could be the locality, languages known, many different ways people can be connected to each other, related to each other, associated with each other, or belonging to a particular organization. Anyone can be part of any different number of organizations. So if two people are related, if they are part of the same organization, so how many such possibilities are there? We can identify for a particular relation, we can find as many pairs as possible. The pairs are connected with the help of a line. So we get the graph structure, which is model of the relationship. It is also known as network. There is another representation. There are many ways of representing these relations. So we just take grouping them. We just two people, and the same thing what we had seen earlier can be grouped in a different way. So it is nothing but you take two elements from the set of n elements, and if in case they are related as per the instruction that is given, as per the relation that or the rule that is given, in case they are related, we are clubbing them, we are making them in one set. So this is another representation. We have set of some people and you pairwise arranging them. First two are friends, are related to each other, connected, some association they have. So we list all the elements in that. Three representations we had seen. By joining each pair by a line, or grouping them, circling them, or arranging them pairwise and listing it, listing the entire collection of pairs. So this relation need not be with just two elements alone. As I was hinting you earlier, you may be part of different organizations within the college itself. One person may be part of NSS. That person, same person, can be part of the cultural team. It's part of a political party, science forum, again mathematics club. Not all would be in all. Therefore, we would say all those people belonging to, we take a cross section, a subset of the entire group of students of St. Thomas College. Then we check who are all part of a particular group. If some of them are part of a particular organization, association, we just club them. We just group them. And then we can identify. So you can see this person who is on the center is actually part of multiple organizations, multiple subsections available. So different representations are available. It is not just two elements alone. When it comes to more than two elements, the graphs become much more active, much more representative. We call it as hypergraph. Only two elements are in each of the relation. Just two elements are connected to each other is called normally with name graph or network. In case more than two elements form part of a particular relation, grouping, or circling, we call it as hypergraph. So our ordinary graph is nothing but a hypergraph wherein which each pair, each subset will be having exactly two elements. From this idea comes the new concept, which is in fact, as far as our topic is concerned, line graphs. So suppose that we have this pairing. Now look at this first two, then number second, third, and fourth. There are four pairs available here. But the first and second, there is a common element, common person. Second and third, there is a common person. And then first, second, third, and fourth, there are common people available. Therefore, we can see, although we have taken two element subsets, these two elements themselves are also related because there are common elements available. This is the motivation behind the idea called line graphs. Line, the word came from this particular representation of graph. Earlier, in the initial years of graph theory development, the objects were considered as dots and the relation was represented with the help of a line. So now, when we are looking at these relations themselves are related or not, that means in such a case, if they are related, we call them as line graphs. So new graph that is generated, that would have its vertex set, the elements consisting of all the pairs available there. How many ever pairs are there, we take that. And their relations can be represented with another. So it is a relation on a relation. We can go to several levels like. After that, again, we can go with that. Line graph of line graph. I call it as a line graph. I gave you the reason why it is called line graph, because initially it was every edge or relation is represented with the help of line. Therefore, from the lines, the edges are obtained. That is what we call line graph. So this is a sample graph that is available here. This is a collection. We are representing them with, so whichever pairs are having a common person available, at least one common person available, we'll club them. We just group them. So these two and nothing else. So in fact, if you are looking at theoretically in an algebraic fashion, we call it as collection of two element subsets of a graph. That is a graph. Not all the collections. If the entire collection is having all the two element subset, it becomes a complete graph. We have NC2, number of two element subsets are available, every pair. But in a general relation, all pairs need not be related to each other. So there, a non-trivial, a non-complete graph comes to existence. For example, here, The possibilities are for C2, but we have just relation here. AB, BD, and BC is not available here. So we get a subgraph. We get a sub-collection of all the pairs available there that is consisting of exactly 4 elements. So we can, as I've hinted you earlier, theoretically, if you're looking at, we can go for k element subsets also. If the vertex set is having exactly n elements, or the cardinality of V is equal to n, we consider a relation consisting of k elements, or at most k elements. We can think in both ways. K elements, exactly k elements, and at most k elements, and then we check whether between them any pair of any collection intersection is empty or not. Intersection is non-empty, then we connect them. So we'll get a. This is another collection, sub-collection available here. 3 element subsets available and 2 element subsets. There is one, the first set is with 3 elements, second set is with a 3 element, third set is consisting of just 2 elements, and fourth one is. So they also can be related if there is at least intersection is non-empty. We can say A, B, C as well as ACD are related. ACD and AD are related. At least one only is required. AD, BD, and we can have, whereas A, B, all of them are related. Representing relation between 2 element subset of a set. This implies line graphs. Relations between 2 element subsets. I've given you this diagram earlier. You can conceive from there. In actually normal system, we come across actually several works in number theory. Is this screen visible to you? Hello? Okay, come back. Just trying to write, it is not. Okay, so I give an example in case you have a paper and pen. Take down this example. Kindly take a paper and pen. Let's take the elements of a set as natural numbers from 1 to 25. 1 to 25. Identify pairs in that such that they have a great common factor other than 1. They have at least one common factor other than 1. How many such pairs are possible from 25? 1 up to 25 is the element. You can keep on. So 1 is not a member that is related to any other element there, because 1 with any other element, the GCD is 1 only. Now take 2. Every other even number, yes, it's related. 2 is related to every other even number. Similarly, every even number themselves is forming a small subgraph there. Yes. Next is numbers divisible by 3. 3 as a common factor. Like that, you can proceed. 4 as a common factor. 5 as anyone is fine. So see, 5 as a common factor. 7 as a common. All the prime numbers you take in, we can exhaust it. Now what happens is 3 would be related to many, 5 would be related to many, 7 would be related to some. 7 are related to which all element? 7, 14, 21, just 3 elements only. They are related to each other because they are common. There is a C3 that is formed out of. What about 11 onwards? 11 also is okay. 11 is related to 22. But 13 is not like there are. So how many isolated elements are there in such a graph? If you draw such a graph, what are those elements? If you draw like graph like that, 1 is not related to anybody, then every prime number greater than or equal to 13, so which are they? 13, 17, 19, 23. They would become isolated elements. They would not be having any. Is it not? Is that clear? And says from audience, someone, can you draw such a graph and find several things which are not related to each other? I'm not able to use the whiteboard here. I was trying, but then later. Okay, let me share this. I stop this. Um, this must be visible now. Is it visible there? Hello.
Yes, Father, it's visible.
So I was asking you to find out 1, 3, 4, 5, 8, all the elements there. The condition was A, comma B is greater than 1, then A is related to B. So we can join such elements with the line. For example, here, 2 is related to 4. Some fundamental, not a big work as such. 4 related to 6. 2 also is related to 6. Then we have 8 coming up here, and then it goes here. The thing I was mentioning was there is an element 13 here, but 13 and no other number has a prime factor, sorry, a common factor other than 1. Therefore, 13 becomes isolate, 17 become isolate, 19 becomes isolated element, 23 also become isolated element. Everything else have some connections.
Okay, let me share this. I stop this.
Then comes next level, which was line graph I was mentioning. Now we find these connections here. What are those pairs that have a common factor with another pair? For example, 2 and 4 are related here. So we connect with the one example. This one way of getting a. So these people are, their GCD is 2. Now 6 and 8, their GCD also is 2. Now we can connect. The next level connection is consider this 2 as well as this 2. As of course, the GCD is greater than 1, therefore they can be same relation can be applied continuously, and then we can find newer graphs. This is where one way of constructing line graphs. One way of. I'm back to the screen. Is the screen visible to you?
Yes, Father.
Thank you. Now comes some of the famous line graphs. Given any path, the edges are denoted with the color red here. Each of these red line becomes a vertex when it takes a line graph. And then if these two lines have a adjacency, so they are adjacent. It becomes another line graph. So it's an interesting problem actually when we are checking. Given a graph from a family, will the line graph be part of the same family? Family can be defined in whatever way you want. I would now call the family as family of all paths. We can extend that to family of trees, family of purely complete bipartite graphs, family of cycles, family of unicyclic graphs. Different types of family, it depends on your requirement. Depending on the degree, we can decide. Okay, a family consists of all the graphs whose maximum degree is 5 and minimum degree is 2. So which are all those graphs? Maximum degree 5, minimum degree 2. Or the family of all the graphs, the maximum, the number of vertices is at most, let's say 7. So each family take, now take the, so this is a simple question, very preliminary question only, but some of you can try working on if in case you have not come across this earlier. Can you check whether given an arbitrary family, the line graph is a member of that family or not? After the operation called line graph operation, on a graph, we get a resultant, we get an output. Is that particular output a member of the same? We call under this operation, the family of that particular family is closed. We have the closure property. So as far as path is concerned, it is valid. Every path, we get another path only. So keep on, and more importantly, each time when a line graph is generated, length of the path is reduced by 1. Finally, we reach 1. So after several operations, we get a single vertex. What is the number of operations required to make it a vertex? Is there any other graph having this property? In path we can get. Is there any other graph wherein which after several operations we get a vertex? There is another case. Consider this cycle of length 5. We take the line graph, similar as we have done earlier, take all the edges. There are 5 edges. Each edge is represented by a new vertex. And if the edges were incident to each other earlier in the original graph, they are now adjacent. Therefore, the graph that is obtained after this operation is exactly same as the earlier graph. Are there any other graph? Is there a family wherein which the line graph of every graph is that graph itself? It's something like identity function. A function f of x is x itself. Previous case, there was a reduction in size as well as the order. Here, absolutely nothing is changed. Can you explore the families having the same property? It is not the same type of element, exactly the same element. Can you collect all such elements? Which are those elements which is giving us, each one is giving us the same element after this operation called line graph operation? Now the general question is, given any graph, is it the line graph of something else? This is a wonderful result that is found out. These are the 9 graphs which cannot be generated from any other graph. Generated in the sense applying this operation of line graph. We cannot get these elements. Any such system is known as forbidden property. In this case, we call these are, as far as line graph operation is concerned, these graphs are forbidden graphs because given the entire family of graphs, these are the elements which cannot be obtained by applying the line graph operation to any of the graphs. So I go with something else now called superline graphs. This is comparatively a newer area, but not very old, not very new too. So somewhere in between, around 27 years, 17 years are over after this. Yes, 27 years are over after the introduction of this. 1995, this idea came into existence. But very less work only is done. Only one book has come out as well as some papers. Can we consider more edges forming part of this? I was mentioning about hypergraph concept, where number of vertices are forming an edge or connection when it is not two. More than two is permitted. So we take k element subsets and exactly k element subsets. Now take this. These are some of the subgraphs of this particular. So we can make them connected to each other depending on. So this is a particular case where in which at most, 5 vertices are there. At most 3 edges are available there. So this has got 3 edges. This has got 3 edges, 2 edges and 2 edges. But we can find an immediate association among these members. There is an edge here that is in brown color. It is available here. There is a black edge here. There is a black edge here. There is green available here. Red and red are like available. So, but these two do not have an association. There is no relation. I go with the definition given by the original authors, Begga, Beneke, and Verma. Given a graph with at least R edges, the graph should have at least R edges. The superline graph of index R, denoted by the symbol L sub R of G, has its vertices, the sets of R edges. Every R element edge set we take. With the two adjacent, if there is an edge in one set adjacent to an edge in another set, there is an incident relation that is coming there. So in connection with this one, what is line graph itself? Instead of R, we'll have LR of G has its vertices, the sets of R edges of G. Given a graph G, take R edges from there. In case of line graph, we are taking each edge from there. So what is the R value here in case of our line graph? In case of line graph, what is the R value? It is nothing but 1, L1 of G. So L1 of G is nothing but the line graph. This is the reference. Can you see it? Please note down. It's a very interesting paper, and then the work is connected to this one only. So consider these edges. I am creating a relation among these members. Just an incidence relation was more than enough, but the moment there is an edge common, immediately we can connect. So we get a new graph that is a complete graph. That's an interesting case. In not all cases, we may get a complete graph. A new graph is generated. So they have identified a parameter associated with this LR of G called superline graphs, called line completion number. Line completion number, LC of G, of a graph G is the least positive integer R for which LR of G is a complete graph. In this case, we had seen that. We have taken 4 edges, 4 subsets there, but it is not exactly our number of edges here. We have varied. So the question here in line completion number is the least positive integer R for which LR of G is a complete graph. So what is the possibility? You can take is this visible?
So consider these edges.
Is it
Can you
visible,
add-
sir?
No, further. Can you add one more?
I am creating a relation among these members.
Yes, for this is happening now.
Just an incidence relation or more than
Is it visible?
there is a complete graph.
Yes, Father. Is it visible now?
So we take the case of a graph. If I take the line graph as A, B, C, D, and E, A and B are related, and B and C are related, B and D are related, D and C are related, D and E are related, and A and E are related. So this particular case, this is nothing but L1 of G. If you have taken L2 of G, what are the possibilities? AB, AE, AD, taking element, 2 element subsets of the edge set, AD and AC. Then comes BE, B and E edge together, BD, BC. Then comes CD. These are all the possible two-element subsets. AD is available there. ED, EC is C is required. EC, yeah, let's try with this. Now they are related if any two edges are. So immediately we can see there is no relation between A, okay, AE and, but they are last. So all are connected. AE, this is the combination available. Then it is related to B, it is related to D, it is related. If A is there, automatically E is related. I'm trying to take anything other than AE. So B and C, when it comes, these two are adjacent here. B and D is adjacent. C and D also is adjacent. Therefore, it's not possible at all. That means this becomes a complete graph if you draw. Everything is related to each other. So here, L, the moment you take L2 of G, that becomes a complete graph. L2 of G. This particular number, if you take anything more than that also, it become a complete graph. The question is, what is the smallest number of edges that can be chosen such a way that the graph becomes a complete graph? And back to the old screen. Is it available there?
Yes, Father.
AE,
Thank you. Now the question is, for this R, what is the least number R can be taken if you consider in this manner? That means line completion number. Should we take all the pairs? Here itself we had seen a graph with 5 edges. When you have taken 2 element subsets, we got a complete graph. So is there a bound in general? Of course, there is a bound that is found out. Line completion number is less than or equal to CEL of cardinality of edges set by 2. That means if you take the half of edges, some way at least one edge is related to another edge. That exactly is that we have seen earlier. If you take the cardinality of the edge, the size of the graph by 2, that gives a interesting bound. So you take a collection of E of G by 2 edges, all such possible edges, if we connect them, that invariably become a complete graph. The question is a super bound. Its bound is extreme. We don't have to reach up to that. What are the other possibilities available there? There are some known results. In the case of complete graph, path, cycles, wheels, people have worked out only less than 10 pairs are available in this area. Finding apart from this particular, even I mentioned you later, complete bipartite graph, the result is not available. Generalized, complete bipartite. So there are some non-results associated with this. Line completion is 1 if and only if G is either K3 or a star K1S when S is greater than or equal to 1. Line completion number 1. That means we just need to take one edge only because that is going to give us K3. When it comes to K4, it is not true because there are two edges which are parallel to each other. In K4, when you take, they will not be adjacent. So first level, it will not be. That means just take the line graph, it becomes a complete graph when it K3. Same is the case with star also. Now, if G does not have 3K2 or 2P3, 3K2 means 3 independent edges, 1P2, P2, P2 like that, or 2P3s, path of length 3, path of length 2. P3, number of edges is just 2. We have 2 P2s independently available there. Then this would not work. In all other cases, the line completion number is less than or equal to 2. Now, line completion is less than or equal to 3 if G does not have any of the following as a subgraph. 4K2, K2 join K12, 2K3, K3 join P4, K3 join K13, 2K13, K13 join P4. And the bounds are very large when it comes to some other. These are some of the proved elegant results. Line completion is m minus 1 when P3 G is either P3 corona m minus 2 K2 or 2 P3 corona m minus 4 K2. That minus minus is m minus only. And when line completion number is m and G is mk2, m distinct edges. That's a graph. These are non-results as far as bounds or different estimations are available. Among the few graphs where the line completion number is already available are these graphs. Apart from this, some more are also available, which I would show you later. Line completion number of path is floor of n by 2. Same is the case with cycle. You can easily verify that. Take a path, you odd and even there is a. So if it's odd size, exactly half you take, they are adjacent to each other. If the number of edges is an even number, 10. Take 5 edges from left hand side, 5 from right hand side for a path, they would be adjacent. That is more than enough. Everything else have a common edge available. Therefore, it becomes a complete graph. K2, in case of Kn, K3 we had seen that it is going to be 1. But whereas when it comes to a complete graph, Kn, the value is P choose 2 plus 1, where P is of the form n by 2. For fan graphs as well as fan graph, wheels you must be remembering. Wheel graph. For wheel graphs, it takes time, so I come back to that. Wheel graphs, that a cycle joined with the vertex. So it becomes wheel graph. As well as fan graph, remove one of the rim edges of a wheel, you get the fan graph. The line completion number is nothing but floor of 2t by 3. Then there is this windmill graph, MT. Windmill graph is a wheel. Some people call friendship graph also. Yes. Wheel where in which alternate rim edges are removed. For that, line completion number is 3t by 4 plus 1. We also have worked on this area. In fact, it came out as an MSc project. We got the article published in a very good journal. It is an exhaustive work, and we found out the line completion number of Pn cross Pm. The grid is nothing but the Cartesian product of two paths. It would be of this shape. What exactly is the line completion number? Suppose we are divided into multiple cases. Several sub-cases we have found out. The result is coming in this manner. Pn, this entire paper contains only one result. This is the result. But it has got different ways of, we can search for this article. It is available in line completion number of a grid graph, or line completion number Pn cross Pn, came in communications and combinatorics and optimization, volume number 6, issue number 2, 2021. So these are the subcases available there. Pn, a path with n vertices, and Pm, a path with m vertices. The line completion of the grid graph Pn cross Pm is 0 when n is equal to m is equal. That is just one vertex only. In itself, there is no requirement of taking anything else. It is maximum of the floor of maximum of n comma m by 2 when exactly one of n or m is 1. That is, in fact, it is nothing but path graph. Third case is when n and m are even. The value is slightly large. Mn plus 1 minus m plus n by 2 minus minimum of n comma m by 2. The fourth case is when neither n nor m is 1 and both are odd. N and m are odd. Third case is both are even. Fourth case is both are odd, but none of them is 1. If anyone is 1, it becomes the second case. Mn minus m plus n by 2, because both are odd, that is that is an integer, minus minimum of n comma n plus 1 by 2, because both are odd. So that also is an integer. Finally, in fact, the third case was really tough for us. If they are of opposite parity, that means 1 is odd, m is odd, and n is even. Or n is even and both the cases it's same. And in both cases, neither n nor m is 1. If that is the case, it falls into the second case. Mn plus 1 minus minimum of n comma m minus seal of maximum of n comma m by 2. So as I mentioned earlier, many works are not yet solved. These are probably a class of probably hypercubes are solved. So we got inspiration from the hypercube. And few other classes are also over. As I was mentioning to you earlier, complete bipartite graph, the work is not yet completely solved. Some cases of complete bipartite graphs are solved. And you have several families of graphs, classes of graphs. The work is not yet complete. As part of a project, small or big, independent of the level in which you are doing the studies, doing the research, you can think about. Even you can take it as a pastime work. When there is nothing else to do, you can try working on this, taking the subsets and seeing whether what combination, which way we have to. It's all given a graph, partitioning them into pieces, such a way that that particular partitioning comes. No way we can take the partition into 2 such a way that there is no adjacency available there. There is no adjacency available. Such a partition, take all the collection, it will not be a complete graph. So that we are looking forward to that particular partition, although we have already been given the upper limit, upper bound. That is seal of number of edges size by 2. So we take anything less than that from there. keep finding around, and we would be able to get that. So this is a recent book that has come. This is the only book given, and it just came in last year. It is actually written by the authors who have actually initially coined this idea, superline graphs. So it's an exhaustive work on, as far as the current literature is concerned, almost everything of this idea on line graphs and line diagrams we can get. In between, they have mentioned about superline graphs as well as line completion number. They have included our result also in it, Binake as well as Bega. Thank you. Any questions? No.
Can try working on this, taking the subset and seeing whether what combination, which way we have to. It's all given a graph, partitioning them into pieces, such a way that that particular partitioning comes. No way we can take the partition into such a way that there is no adjacency available. There is no adjacency available. Such a partition take all the collections, you will not be a complete graph. So that we are looking forward to that particular partition, although we have already been given the upper limit, upper bound. That is C of number of edges size by 2. We take anything less than that from there, keep finding around, and you will be able to get. So this is a recent book that has come. This is the only book given, and it came in last year. It is actually written by the authors who have actually initially coined this idea, superline graphs. It's an exhaustive work on, as far as the current literature is concerned. Almost everything of this idea on line graphs and line diagrams you can get. In between, they have mentioned about superline graphs as well as line completion number. They have included our result also in it. DNK as well as beta. Thank you. Any questions?
Any questions, please? If you have any questions, you are free to ask. Okay, Father, I think they are all clear. We just wanted. Father, respected Dr. Father Joseph Kuritra, my dear colleagues, they are all here. We just wanted, and my dear friends, and also students. Here we are on the ending session. Dr. Father Joseph Kuritra, my dear colleague, of thanking Dr. Father Joseph Verghese for his invited talk, a very good invited talk on some bipartite graphs which are having different applications in our day-to-day lives. I think Father's talk was very nice, and we were hearing it online outside, and it was informative for the students, I feel. On behalf of the Department of St. Thomas College Mathematics, we render our heartfelt gratitude to Reverend Father Joseph Kuritra, CMI, Director of Research, Christ University, Bangalore, and we are indeed proud that we are having Father among amidst us. And thank you, Father, for spending your valuable time. I think the Father was rushing from somewhere and he was coming inside the room and was just clicking off. And it was a very beneficial talk for our students because they are up to learn graph theory in their masters and also in the UG. So I hope all the students who are attending the conference benefited from the talk and they could at least hear something regarding graph theory. And you wholeheartedly thank you, Father. Thank you so much. Thank you. Thank you, Father. Father, for spending the valuable time, I think the Father was working from somewhere and he was coming inside the room and was just sitting off. And it was a very beneficial talk for our students because they have to learn graph theory in their masters and also in the UG. So I hope all the students who are attending the conference benefited from the talk and they could at least hear something in graph theory